Welcome back to Neural Intel. Today we're diving deep into a really fascinating technical challenge in the world of large language models, LLMs.
Yeah, we're looking at how these models sometimes just make things up. The phenomenon known as hallucination.
Exactly. And you've brought an article from Amazon Science detailing some new research on this.
That's right. It covers work presented at EMNLP 2024 by Erica Salinas and Shayan Ali Akbar. They've developed this novel approach called Hallumeasure.
Hallucination.
Okay, and our mission today is really to unpack the technical details of how Hallumeasure works, how it tries to automatically spot these LLM inaccuracies.
Great. So let's start with the basics, just to frame the problem. When we talk about an LLM hallucinating, what does that actually mean in practice? Can you give an example?
Sure. The article uses a good one. Imagine asking an LLM about drug interactions with, say, St. John's wort. Ideally, you'd want it to check a proper medical database, right? But the research points out many LLMs don't do that. They might generate a list based on patterns they've seen in text, mixing real interactions with possibly incorrect ones.
So it's not querying a database, it's sort of generating what looks like a plausible answer based on its training data.
Exactly. It's like an informed guess, but without that crucial verification step. And that can lead to really unreliable outputs, especially in sensitive areas.
Like healthcare, as you mentioned.
Yeah.
That sounds like a significant technical barrier to wider use.
It absolutely is. If you can't trust the output, particularly for critical applications, it limits adoption. So the big challenge here isn't just knowing they hallucinate, but having solid technical ways to automatically find and measure these errors.
Right. Detection and measurement is the first step towards reliability.
Precisely. That's where Hallumeasure comes in.
Okay, so how does Hallumeasure tackle this? The article mentions a three-pronged approach. Let's break that down.
Yeah, it combines three core techniques. First, there's claim-level evaluation. Second, it uses chain-of-thought reasoning for classification.
And thought, right.
And third, it performs a specific linguistic classification of the hallucination error types. These three work together.
Interesting. Let's start with that first one. Claim-level evaluation. What does that involve?
So the idea is to take the LLM's entire response and break it down into smaller pieces, which they call claims.
Claims.
And they define a claim as basically the smallest unit of information you can actually check against the source material, the context. Usually like a simple statement with a subject and a verb, maybe an object.
Okay, like dissecting a paragraph into individual factual statements.
Pretty much. So if the LLM says the Eiffel Tower is in Paris and was built in 1889, Hallumeasure would likely split that into two claims. One about the location, one about the date.
Got it. And why do that? What's the advantage of evaluating claim by claim instead of the whole response?
Two main technical benefits, really. First, better accuracy in detection. A small error might get lost in a big block of text if you evaluate it all at once. Second, it gives you much more precise error localization. You can say, this specific statement is the problem, not just something's wrong here.
That makes sense. Much more targeted. How does Hallumeasure actually extract these claims from the text? Is it another model?
It uses what they call a claim extraction model, but here's the clever part. They don't need to fine-tune or update the LLM's weights.
Oh, interesting. How?
They use few-shot prompting. Essentially, they give the LLM inscriptions, rules, and a few examples of responses already broken down into claims.
So you're guiding the existing LLM with good examples within the prompt itself.
Exactly. It learns the task from the prompt context without needing costly retraining.
Very neat. Okay, so claims are extracted. What's next? This is where the advanced reasoning and claim classification come in.
Right. The next step is to classify each of those extracted claims. You compare it against the context, the relevant, hopefully verify information retrieved for the original query. The ground truth, basically.
Okay, comparing the claim to the source material?
And the model classifies each claim into one of 5 categories. Supported by the context, absent from the context, contradicted by the context.
So directly disagrees.
Yep. Then partially supported, maybe some bits match, but not all, and unevaluatable, meaning you just can't tell from the context provided.
Okay, those seem clear. Supported, absent, contradicted, partial, unevaluable.
Now, initially, the researchers tried just asking the LLM directly, classify this claim, but the performance wasn't quite good enough.
It struggled a bit.
Yeah. So they shifted to using chain-of-thought reasoning, or COT.
Right, COT. We've talked about that before. Remind us quickly, what's the core idea?
The core idea is prompting the LLM not just for the answer, but to explain its reasoning step by step, like showing your work in math.
Yeah.
It forces the model to generate intermediate steps, which often improves performance on complex tasks and makes the output more understandable, more explainable.
So how did HelloMeasure apply CoT to classifying these claims?
They developed a specific five-step CoT prompt. It mixes few-shot prompting, showing examples of classified claims with the reasoning with explicit instructions.
Instructions like,
Instructions for the LLM to carefully check the claim against the context and explicitly write down why it's assigning a certain category, supported, contradicted, etc.
so forcing it to justify its classification, did that actually improve things? Did it work better?
It did. The article mentions they tested this on the SumEvol benchmark dataset.
Which is for evaluating text summarization
Yeah.
quality, right? Factual consistency is key there.
Exactly. And using this few-shot CoT approach, HelloMeasure boosted performance. They saw a 2 percentage point increase in the area under the ROC curve from 0.78 to 0.8.
Okay, 0.78 to zero point 0.8 ROC AUC. That's a tangible improvement in automatically spotting these factual errors.
Definitely. It shows the CoT prompting really helped nail down the classification accuracy.
So we've got claims extracted, then classified using this step-by-step CoT reasoning.
Mhm.
What about the third prompt, the fine-grained error classification? Why go deeper than just supported or contradicted?
Well, the researchers figured that just knowing a claim is, say, contradicted is useful, but it doesn't tell you how it's wrong. What kind of mistake is the LLM making?
Okay. More diagnostic detail.
Precisely. So they developed this new taxonomy of 10 distinct linguistic error types. They came up with these by looking closely at the patterns in actual LLM hallucinations.
10 different types. That sounds quite detailed. Can you give an example?
Sure, the article mentions temporal reasoning errors. That's like the LLM saying a new technology is already being used everywhere, but the source text actually says it's planned for the future.
I see. Getting the timing wrong. What are some others?
Things like entity errors, mixing up people or places, or overgeneralization, taking a specific case and presenting it as a general rule.
Okay, I can see how knowing that level of detail would be much more helpful than just a simple wrong label. What's the technical value for LLM developers?
It's huge for diagnostics. If you see that your model makes a lot of, say, temporal errors, you know where to focus your improvement efforts. Maybe work on how it processes time-related information.
Right, it guides the debugging and retraining process. Instead of just knowing it's hallucinating, you know what kind of hallucinations are most common.
Exactly. The article gives that example too if you see lots of contradicted errors popping up late in a long conversation.
Then maybe limiting the conversation length could be a targeted fix for that specific model and problem.
Precisely. It allows for much more targeted, data-driven improvements rather than just general tweaking.
So after doing all this claim extraction, code classification, error typing, how does HalluMeasure summarize the overall level of hallucination?
It calculates an overall hallucination score, which is basically the rate of unsupported claims. That includes everything not classified as supported.
So absent, contradicted, partially supported, unevaluatable, all count towards the hallucination score.
Correct. And alongside that score, you get the distribution of those 10 error types, which provides that deeper qualitative insight into what kinds of mistakes are happening.
It really sounds like a comprehensive system, getting both a number and the story behind the number. Did the article mention where this research might go next? Future directions?
Yeah, they touched on a few important areas in responsible AI research. Things like reference-free detection.
Detecting hallucinations without needing a ground truth document to compare against. That sounds challenging.
Very. Also, dynamic few-shot prompting, making the prompts adapt automatically, and integrating these detection methods into more complex agentic AI systems.
So acknowledging the problem keeps evolving.
Definitely. They recognize that generative AI risks aren't static, so the techniques to manage them need to keep advancing too.
Okay, it's really clear how HelloMeasure offers this detailed technical framework, breaking things down into claims, using CoT for better classification, and then getting that fine-grained error analysis. It does feel like a significant step.
I think the really key technical takeaway here is that level of granularity. We're moving past just saying it hallucinates to understanding how and why.
Right, getting under the hood of the errors.
And that detailed understanding is what developers really need to build more reliable AI. It's fundamental.
Which naturally leads to a broader thought. How might these kinds of techniques, breaking down outputs, classifying errors, analyzing error types, be adapted for other AI systems?
That's a great question. Could you apply similar principles to, say, evaluating the reliability of computer vision models?
Yeah.
Or maybe reasoning systems in robotics?
Or even in completely different technical fields outside of AI. It feels like a powerful diagnostic pattern.
It does. It's definitely a fast-moving space, and getting a handle on these fundamental approaches for measuring and understanding AI behavior, like Measure does for LLMs, seems absolutely key to navigating where it's all headed.